So for the rest of this quarter, or at least most of the rest of this quarter, we're going to be looking at applications of integrals. And the first one here in section 6.1 is area between curves. So the idea is you've got a couple of curves. Let's say this is y equals f of x. And you've got some other curve maybe down here, y equals, see if I can do this, y equals g of x, and you've got some starting point here, x equals a, and some ending point, x equals b, and you're looking for the area in between these curves. Well, it's really not too hard to work off of what we've already done to say, hey, if you just gave me one function, I'd be able to find the area underneath the whole thing all the way down to the x-axis. That would be the integral from a to b of, why is this doing this to me? I seem to be ahead of my computer. Of f of x dx, right? The integral of f of x dx. And you say, oh, but I could also find this area down here, and the area between g and the graph here. And so that would be the integral from a to b of g of x dx. And if I just subtracted the area underneath this bottom one from the area underneath the top one, then that should end up being the area in between. And it is. It is. The thing is, we could write this as a single integral because the interval is the same. We could just write this as the integral from a to b of f of x minus g of x dx. And actually, once we write it that way, it gives me another way of thinking about this. I'm going to redraw the picture here. Not with a eraser. This is trying to catch up. I'm not exactly sure what's going on. There we go. We're going to go from a to b. I've got the function f on the top. I've got some other function here, y equals g of x on the bottom. And one of the themes that you'll notice as we go through chapter 6 and then chapter 8 is that the way we do a lot of things is we chop them up into little pieces, figure out each little piece, and then add them back together again. Now, what I've done so far was sort of the whole, hey, I can calculate this whole area, I can calculate that whole area. But remember that we're calculating areas by chopping them up into little rectangles, which makes me then think of this, is that I want to think about calculating this area in between by little rectangles. For each value of x between a and b, I'm going to have a little rectangle whose height is determined by the top function, well, the y value up here and the y value down there, whatever the difference is between those two values. And so the height, so for a given value of x here, this is g of x, y equals g of x, this is y equals f of x, so the height from between those two functions is, in fact, f of x minus g of x, the difference in the y values. If I then give that height a little bit of thickness, the area would be that height times dx. And if I add up all of those little bits of thickness all the way from a to b, not those little bits of area, these little bits of area, right? This is a height, this is a little bit of thickness, the product is a little bit of area, and I add up all those little bits of area all the way from a to b, I end up with the area between the curves. Okay. So, for instance, let's do one of my favorite examples here. Let's take a look at y equals x and y equals x squared. They intersect here at 1, 1, and they intersect there at 0, 0. I want to find the area by adding up a bunch of little rectangles. So for every value of x between 0 and 1, I've got one of these little rectangles. Now, generally I don't draw them all in because there's too many of them. But to give you an idea, for different values of x, some of them are kind of short, some of them are kind of tall. They get kind of short again up there. What's the height? What's the top minus the bottom? Well, in this region here, the y equals x is the top. y equals x squared is the bottom, so x minus x squared is the height of each one of those rectangles. If you give it a little bit of thickness, dx, and then integrate from 0 to 1. 0 to 1 because that's where the region starts and that's where the region ends. Now, I'm very happy at this stage of the game for you to do these integrals by hand if you want, or to do them with your calculator. I would opt for the calculator myself. Generally, this one's easy enough to do. In fact, actually, this one is so easy to do, I'm just going to do it. Right? It's x squared over 2 minus x cubed over 3, evaluated between 0 and 1. So it's 1/2 minus 1/3 minus, which you get when you plug a 0 in, which is 0 minus 0. So it's a half minus a third, which would be 1/6. So the area there is 1/6 of a unit, whatever, sorry, 1/6 of a square unit, whatever this length is. Is that 1 inch? Is that 1 mile? I don't know. But whatever that is, squared, 1/6 of that. Actually, I look at, if you're drawing this whole square, this 1 by 1 square, we're saying that the area of this thing is 1/6 of that whole area of the square. Seems about right. Anyway, 1/6. Area between curves. Let's do one more example. Another one I like is, if you look at the sine curve and the cosine curve, they kind of intersect in some interesting ways. Here's y equals sine x, and here's y equals cosine x. I've got to get some points of reference in here. Y equals cosine x kind of comes in like that. Goes up. I want to find this area right there. So the question is where, this is y equals sine x, this is y equals cosine x. The question is where do they intersect? Well, they intersect when the sine is equal to the cosine. I think that happens just like with a 45-degree angle here, 45, 45, 90. Actually, but we're going to do everything in radians. I'm doing calculus here. Everything should be in radians. So this is at pi over 4. Pi over 2 is right here. Pi is right there. So this should be, must be in the third quadrant, right? Because, oops, what do I have here? In the first quadrant, you've got, at that pi over 4 line, you've got y over r is the same as x over r, so sine and cosine are the same. Down in the third quadrant as well, you've got negative 1 over radical 2 and negative 1 over radical 2 for sine and cosine. So that must be at, let's see, that's 1 pi over 4, 2, 3, 4. That must be 5 pi over 4. So I want to find the area in between those curves. Now, one of the things I like about this example as well is that this allows the functions to be actually negative. And so the idea of area underneath, we can get around by doing this difference in the top minus the bottom. Because I'm going to look at an integral here where each one of these little rectangles, each one of these vertical lines I drew, you give a little bit of thickness to make it a rectangle. The height of the rectangle is the y value at the top minus the y value at the bottom. The top function here is sine x. The bottom function is cosine x dx. And I'm interested in this, the dx is to give it some thickness. I'm interested in this from pi over 4 to 5 pi over 4. Okay. Notice that even when some of these are negative, or both of them are negative, if you do the top one minus the bottom one, right? If you're looking at something like this and you say, hey, I've got a height of -2 and I've got a height down here of -4, you know, what's the height between them? Well, it's the top minus the bottom. -2 minus -4 actually ends up giving you a +2. Top minus the bottom is always going to give you that positive, even if both of them are negative. Or if one of them is positive and the other one is negative, still the difference between them is the height. So this top minus bottom definitely takes care of whether you're above the axis or below the axis or straddling the axis. It doesn't matter. Now we need to do this integral, And I am going to break down and use my calculator on this one and try something. Alright, so I'm going to try this on my calculator. I'm going to do math, function int. I've got sine of x. I'm still in radian mode from the last time I used this, minus cosine of x, comma, the dx, so you just say x, comma, I'm integrating from pi divided by 4, comma, to 5 pi divided by 4. 5 pi divided by 4. And enter. And it gives me a value of 2.824. Actually, you may not recognize that, but I do recognize that as, oops, what just happened here? Come back. I'm just curious. I think this is 2 times the square root of 2. 2 times square root of 2 should be the same number. Yes. Anyway, the area there is 2 times the square root of 2. Area between curves, top minus bottom times dx, integrate from start to finish. Anyway, we're going to take a look at some of them with some other variations here in the next video.